Hi, everyone. Thanks so much for joining. My name is Darcy Kahn. I lead the cell-based assays here at Mosaic Biosciences. And today we're going to be talking about T-cell engagers. Specifically, this talk is about how you actually characterize a T-cell engager functionally, not how you engineer it. So if you're interested in the bioengineering of T-cell engagers, that content will not be in this talk. But if you're interested in functional characterization, we will get into a lot of details about that. Um, all right, so quick roadmap so you know where we're headed today. We'll start with why functional characterization matters in the first place, and why it matters so much for T-cell engagers specifically. Then I'll walk through our platform and our design philosophy. From there, we'll build up a functional profile step by step. For this, we're going to be using an approved DLL3 targeted T cell engager. That will be our benchmark through the whole talk and all of the data. And then we'll wrap by putting it all together and talking about, where this actually plugs into a program. And I'll close out with a few of the questions that we get asked most often when we do this kind of work. All right, so let's start with the obvious question. Why do this at all? You already ran your binding assays and you know that your molecule engages its target. The thing, though, is that while binding tells you that it connects, functional assays actually tell you what that connection does. Biophysical data confirms engagement, but functional assays close the gap. They do that by testing that engagement in a biologically relevant system, where the question is not just whether the molecule binds, but whether it drives the right response. And that divergence matters most when the cost of being wrong is highest. So these are in things like picking a lead, deciding what is developable, and building confidence that in vitro results will actually translate in vivo. So you see the same principle in T cell engager development all the time. Two molecules can have very similar affinity for their target and produce very different amounts of actual killing because things like epitope location, the geometry of the synapse, these things determine whether engagement actually translates into a productive killing signal. So, a molecule can bind beautifully and still underperform functionally. In rarer cases, it can be the opposite, where it can bind modestly and outperform on function because the geometry happens to be just right. And so binding will tell you that it connects, but it doesn't tell you what that connection does. So all of that is true for biologics in general, but it's especially true for T cell engagers, and that's why I want to pause here. So a T cell engager isn't a simple binder, it's a conditional agonist, meaning its mechanism depends on the biology of the two cells it brings together, right? So things like antigen density on the target cell, effector to target cell ratio, synapse quality, what's happening to the T cells afterward. These are all things that are a part of a T cell engagement. And that's why the functional picture for a T cell engager is broader than for some other modalities. You know, cytokine release, serial killing, exhaustion, those aren't just bonus readouts for T cell engagers, they're direct consequences of the mechanism. And so they tell you things that other biophysical measurements just cannot. Um, and I wanted to pause here to mention that this matters beyond just the science of it all. FDA guidance on bispecific and agonist biologics points to in vitro functional assays as a part of how you justify your MABEL dose, MABEL being the minimum anticipated biological effect level. And this is for first in human trials. So it also reinforces the need for a quantitative biological potency assay as a program advances and you get into regulation. So the functional package that you build early is not just helping you make internal decisions, it becomes a part of the evidence base that supports your clinical strategy. Okay, so that's the why. And now I want to get a little bit into the how. So Our platform at Mosaic is modular and it's flow cytometry based. And I want to spend just a minute on what that actually means because it's the thing that makes it, I think, very, very useful rather than it just being kind of like a menu of assays. So, what I mean by modular is that each readout, so that being cytotoxicity, activation, expansion, cytokines, and so on, they stand on their own. If you just need one specific question answered, you can run one assay. But they're also built to complement each other so that when you do run them together, each one adds a different layer of context on that same underlying biology. So, while activation tells you engagement is happening, expansion and proliferation tell you whether that engagement is durable. We've got cytokines that can tell you about efficacy and risk. So none of them individually tells you everything, but they're designed to fit together into one coherent picture rather than a stack of, you know, disconnected data points. And I think that's the real value of this platform. You're not locked into an all or nothing package, but when you do want the full picture, it's genuinely integrated within the same assay oftentimes, not just, several vendors worth of assays bolted together. So this gets used routinely to support lead optimization, benchmark comparisons against approved or clinical stage molecules, and then of course preclinical decision making more broadly. Um, and which pieces you pull in really depends on the stage that you're at and the questions you're actually trying to answer. Okay, so before we get into the individual assays, I just wanted to walk through the system underneath all of them because the same core setup shows up again and again. So to set the foundation for the setup. So we use primary human PBMCs or isolated T cells as our effectors. Um, Donor strategy and handling matter a lot here. And so I'm going to spend just a second on that because I think it's very easy to underestimate. Not every donor's T cells behave the same way, and how we approach that depends on what stage a program is at, and really what question we're trying to answer. So, sometimes that means a small, well-characterized donor set with specific attributes that are set to get a clean comparison between the candidates. Um, Whereas sometimes it can mean a deliberately diverse panel of donors that can really demonstrate robustness. So, you know, either way, it's a designed choice, and we think about it very carefully. Um, I also wanted to mention when thinking about effector cells that we've at Mosaic, we've also put a lot of work into our isolation and cryopreservation methods, specifically because how you handle these cells before they ever even see a test article or a T cell engager very much affects how they respond. So, a poorly handled donor sample can look like a bad molecule when actually it's just a bad cell prep. I'm not going to get into the specifics of how we do that, but I just wanted to mention how deliberate that process is when planning your experiments. Beyond donors, we then, pair antigen positive target cells with antigen null or irrelevant antigen controls so we can confirm activity is actually target dependent and not just generic T cell stimulation. Um, and we run soluble TCEs across concentration response and E to T ratio curves, always including benchmark and negative controls built in throughout. Um, and then on the design philosophy side, a few things we really think about when we set up these assays. So, concentration response curves, E to T ratio curves, those are going to give you robust comparisons of potency and efficacy. We also use multiple time points when it makes sense because early versus sustained responses tell you very different things, right? So readout selection is really driven by the question you're trying to answer. Something I have already said a couple times and will continue to say. Um, are we interested in mechanistic insight? Are we trying to answer a specific pharmacological question? Or are we really thinking about developability risk? All of those, goals are going to require different decision making on the design philosophy of our assays. Um, I think one more thing before we dive into the data, I just wanted to mention that throughout the rest of this talk, I'm going to use an approved DLL3 targeted T cell engager as our benchmark molecule. Um, as many of you know, using a well-characterized reference, that's important for letting us anchor the data to something very concrete instead of showing isolated numbers without any context. Okay, so the first stop is cytotoxicity. This is the primary efficacy readout for a T cell engager. Target dependent killing is the whole point of the molecule, right? So this is usually the first thing we look at. So in this assay, PBMCs get cold cultured with an antigen positive and antigen null target cells, or using a null test article. We do this in the presence of soluble T cell engager across a concentration response and different E:T ratio curves. As you can see in the data highlighted here, we used 2.5 to 1, 5 to 1, and 10 to 1 effector to target cell ratio curves. With our benchmark, what we see is efficient antigen-dependent killing that holds up even as you see the E/T ratio, as you see decreases, in the E/T ratio. So even at 2.5 to 1, we're still seeing a saturation of the signal at the higher concentrations. And so this tells you that this is a highly potent molecule, not one that only works when you flood it with effector cells, right? So what this actually tells you is quantitative potency and maximal efficacy of target-dependent killing. This is your primary functional benchmark. Everything else we're going to talk about walking through adds context on top of this data set. All right, so next up is activation. So if cytotoxicity tells you the endpoint, then activation will tell you what's happening upstream of that endpoint, right at the point of synapse formation. So we look at activation markers. These can be CD69, CD25, CD71, whatever makes the most sense for your goals. And we look at this again by flow cytometry on a defined T cell subset after TCE-driven cold culture. Here we're looking at the CD8 positive T cells, and we can tailor the specific T cell subset to whatever makes the most sense for your molecules. So what we can see is that our benchmark drives clean, dose-responsive activation, increases in both CD25 and CD71 on these CD3 positive, CD8 positive T cells, and that tracks with dose. What we also notice is that when we're using null controls, non-targeting control molecules, we don't see activation at all. So, what this tells us is that our engagement is actually happening the way we'd expect, and it gives us context for interpreting everything else downstream. If your data on your killing assay looks off, this kind of activation data can help you figure out whether the problem is upstream of the kill step or somewhere else. Okay, moving on to expansion. So this is about whether sustained engagement actually translates into more T cells over time, not just more activated T cells. So what we do here, as you can see in the data, is we run multi-day co-cultures and we quantify T cell frequency or counts by flow cytometry across defined subsets. So here you can see we had readouts at 24, 48, 72, and 96 hours. With our benchmark molecule, what you can see is dose-dependent CD3 positive T cell expansion out to about 48, 72 hours. And then it plateaus. We don't see any further increase by 96 hours. This really lines up with loss of the ongoing target engagement over that window because the effector cells are eliminating those target cells, and without the engagement, we no longer have the expansion. What we can see in the data that's showing the response to null control is that we don't have dose-dependent expansion. And this is exactly what you want to see in your negative control, right? It confirms that this is target driven. I'll mention, because this is important, that viability and those null control stays high the whole time. That matters. It rules out um, an alternative kind of explanation for this plateau. This isn't that the effector cells are just dying off from a lack of activation. They're alive and they're simply not expanding because they don't have that same target engagement that the cells in the other test group do. And so that's what tells you the effect is real biology and not just an artifact of unhealthy cells. And so, you might wonder like why this actually matters for your program. And I think that, while activation can tell you that, the molecule flipped the right switch, expansion tells you something different and, possibly more important when thinking about it in a clinical setting. It tells you whether that engagement is strong and sustained enough to actually build up this army of T cells over time, not just a spike and fade effect. And that distinction is a big part of what separates a molecule that looks good in an acute assay from one that can actually like sustain a response in a patient. We'll talk a little bit more about that in a couple of slides. So this next data set is looking at proliferation. This is, I guess, a companion to expansion, but it's asking a slightly different question. So what we're looking at here is the increase in cell numbers actually coming from division, and distinguishing that between something else like preferential survival or redistribution of existing cells. So what we do here is we label PBMCs with a proliferation dye before cold culture, and then we can track dilution across the T cell subsets over multiple time points because the signal of that dye decreases with every proliferation event. So really useful tool for looking at proliferation by flow cytometry. So what you can see in the data is that with our benchmark, we have clear progressive cell trace dilution across 24, 48, 72, and 96 hours with barely any effect at 24, and we start to see it progressing slowly over time. And so this confirms that the T cell increase we saw in the expansion is being driven by active division, not just survival. So when you put those two things together, you've got real confidence that what you're seeing is genuine driven expansion. Okay, now on to cytokines. So this one matters a lot because it's telling you about both efficacy and also speaks to risk at the same time, right? So what we do in this assay is we quantify cytokine secretion from cell culture supernatants. Our platform is multiplexed using MSD, which is mesoscale diagnostics, and we do this following the T cell engagement driven PBMC target culture. So one point here is just thinking about how much data we're getting out of one assay. We're using the cells that are in that well to understand what's happening at that single cell level by flow cytometry in terms of target cell death, effector cell activation, expansion, all of those things I was previously mentioning. We're also taking that cell culture supernatant out of the same well and getting even more data out of that in the form of these cytokines here that I'm showing. So what we can see in the data is that our benchmark drives what I'd call an effector skewed profile. So we have high interferon gamma, high granzyme B, moderate TNF alpha, and importantly, limited IL-1 beta, IL-6, and IL-10. So this is exactly the kind of thing that we would expect to see from something that was driving an effector function. And why does this effector kind of profile matter? Because IL-1 beta and IL-6 in particular, those are the cytokines that are most associated with cytokine release syndrome risk clinically. So this readout is giving us both an efficacy signal and it's giving an early read on inflammatory risk, and it's all happening in the same assay. So as I mentioned, it's just a lot of information to get for one experiment. The next assay to consider is looking at longevity and serial killing. So everything that I've shown up to now has largely been acute readouts. So this is where we ask, Does the molecule hold up over time and repeated engagement, or does function start to drop off? So we use extended time point, or I guess re-challenge co-culture formats, where T cells get exposed to fresh target cells multiple times to evaluate whether the killing capacity of that effector cell, of that T cell, um, can hold up. If that T cell can be persistent over time. So what we can see here is that our benchmark molecule has rapid, sustained cytotoxicity across 3 rounds of target restimulation. And then we see a decline in activity over, you know, further extended culture. So we start to see our ability of the effector cell to mediate target cell killing decline and get close to baseline around day 17. So I think this tells you something really important for a T cell engager program. How much repeated killing can you actually get out of this molecule before T cell fitness starts to drop off? And that's going to be directly relevant to dosing frequency, and the durability of your response. And just to mention that this is exactly where a benchmark comparison becomes powerful, not just informative. So all I'm showing here is the benchmark molecule, right? But if you're to be comparing your own molecule against an approved molecule like the one we're using today, and you can show that your molecules has sustained killing capacity for more rounds of restimulation, or can hold on longer before approaching that baseline. That's a big deal, right? Like that kind of difference can translate directly into like real feasibility and efficacy advantages. Um, Maybe that means less frequent dosing, or like a longer functional window per dose. Um, Genuinely differentiated clinical profile. So I think this is a really clear place in the whole functional package where a head-to-head comparison against a known molecule can tell you something a standalone number never could. So this is the last slide. This will round out the functional picture. Um, we're looking at checkpoint marker expression here. So this will give us a phenotypic window into T cell state, specifically whether cells are trending towards exhaustion. So we use a variety of different markers. Here we're using PD-1, TIM3, and LAG3. Again, this is done using flow cytometry. These assays were done following successive rounds of target restimulation. So with anyone less familiar with these, they're often called checkpoint or inhibitory receptors. They're proteins that show up on the surface of a T cell as it gets repeatedly stimulated, in this case, and their job is to put the brakes on that T cell so it doesn't stay activated forever. And we want a little bit of that, right? A little bit of that is very healthy. It's how our immune system normally regulates itself. But when these markers climb and stack up together, it's a sign that the T cell is heading towards an exhaustive state. And it's still alive, this T cell, when it's exhausted, but it's functionally much less capable of doing its job. So these are, really important things to look at when trying to understand the full picture of T cell resilience in your culture. Um, and so what we can see in the data is increasing checkpoint marker expression between days 10 and days 17 of prolonged stimulation, matching the functional data that we saw in the previous slide. And so, this helps give that phenotypic context for the functional decline that we see in a serial cytotoxicity or a longevity assay. Um, so I guess in other words, this is the mechanistic explanation for why killing capacity drops off over time. I think that can be really powerful to show side by side. So I think after showing all of that data, maybe we just step back and put it all together, because no single assay in isolation tells you the whole story, and that's part of what we're trying to describe today. So what we're offering here is that orthogonal functional readouts give you a cohesive view of TCE activity across efficacy, mechanism as well as durability. So cytotoxicity tells you it works. Activation and expansion, that tells you that the mechanism is doing what you'd expect. Um, Cytokines tell you about efficacy as well as risk. And then you've got longevity and checkpoint markers that are telling you how long that function actually lasts and why. So if you put all of that together, you're not just, checking boxes, you're building a real integrated picture of how this molecule behaves in a physiologically relevant system. And so that's the kind of depth that actually really informs decision making, and it doesn't just, confirm engagement. You might wonder where this would actually plug into your program. Um, and it's not one moment, it shows up at a few different points depending on the question you're asking. So in lead optimization, if you're ranking candidates on potency, efficacy, cytokine profile before you lock in a lead, this would, be important to do at that point. If you're trying to do benchmark comparison, you're contextualizing your asset against the approved or the clinical stage molecules like we did today. And in preclinical IND enabling work, this is where you're building the functional evidence base that you will use to support your first in human dose rationale, and your potency assay development going forward. So, the platform is modular on purpose, so you can put in exactly the pieces you need at whatever stage you're at, rather than just treating this as a all or nothing package. I did want to answer a few questions that we get asked a lot. So since we don't have a live room to pull them from today, I'm just pulling from our heavy hitters in terms of what we get asked most commonly. So the first one that we get asked a lot is, how do you handle donor variability? Doesn't that mess with your data? And I spoke to this a little bit earlier, but donor variability is a very real thing. But I, I always push back a little on how the question is usually framed. So donor variability isn't just noise you're trying to control out of your data. If you handle it the right way, it's an important part of building the actual case for your molecule, right? Early in discovery, when you're just trying to differentiate candidates or nail down a mechanism, at that stage, it definitely can make sense to work with a smaller set of like well characterized, known to be responsive donors. You want a clean signal so you can actually compare molecules against each other without like donor noise getting in the way. But as you move closer to IND, the question changes, right? At that point, you don't just want to know your molecule works in this like perfect donor. You want to be able to show it works across a genuinely diverse set of donors, with different HLA backgrounds, different baseline immune states, and because that's the kind of variability you're going to see when this get actually sees patients. So, I think showing a consistent response, across a diverse donor panel is a very meaningful part of building a case for efficacy. Um, and it's evidence that the biology is robust rather than kind of fragile and only working under the most perfect conditions, the most perfect T cells. So the real answer is, which strategy you use kind of depends on where you're at in your program, and what you're trying to prove. And so that would be something discussed early on when designing, the assays. Uh, Another question that we get commonly is, you know, how long does a functional package like this actually take to run? And of course, that just depends on scope. But as a rough sense, a single assay, say cytotoxicity alone, that can turn around in a couple of weeks, including data analysis. The full integrated package we walked through today, all the way out to longevity, checkpoint markers, that's more like 6 to 8 weeks, mostly because some of those readout need extended time and culture, as we discussed. Um, a- a- and this is also assuming, that we've optimized for the right conditions and such. So If you're on a tight timeline, tell us what decisions you're trying to make, and we can usually figure out which subset actually answers that question and can get you there fastest. Um, Another one's about throughput. So, how many samples can we actually get through? What does throughput look like? It's more than people usually expect because, because the platform is flow cytometry based and built around, you know, standard multi-well 96, sometimes even 384 co-culture formats, we can run these at, meaningful scale, comparing many candidates side by side across full concentration response curves in the same experiment, and definitely not just one molecule at a time. So if you've got a panel of candidates you're trying to rank, that's, exactly the kind of scale this is built for. Maybe not when you're in the hundreds, many of candidates, but, if you've narrowed down that list, and you can tell us how many molecules you have and how many conditions you're thinking about, and just reach out with that information, and we can tell you pretty quickly what a realistic timeline looks like. And then the last question would be, how does this relate to the formal kind of like potency assay we'll eventually need for our IND? Um, this isn't just upstream prep work that eventually gets replaced by something more official. In real programs that we've supported, this exact kind of data set, cytotoxicity, activation, expansion, cytokine profiling, has gone directly into a pre-IND submission package itself. Regulators want to see that you actually understand your molecule's mechanism and biological activity before you put it in a person. And so this is precisely the data that does demonstrate that. Um, so yes, one of these readouts, most often cytotoxicity, will typically get carried forward and formally validated as your ongoing potency assay across later phases. But the rest of the package doesn't get discarded once that happens. And it's a part of the mechanistic and functional evidence base that's going to be supporting your dose rationale, and your overall submission. It's not just like a rough draft that stops mattering once you pick an assay. So if anything, I think the broader the functional picture you can show regulators up front, the stronger your submission is. And so, this is real, usable evidence, not just homework you do before the real work starts. To bring it back to where we started, the binding and biophysical characterization can tells you that a molecule connects. Function and really intentional functional assays can tell you what it actually does. And for T cell engagers specifically, that functional picture is not optional. It's core to understanding the biology, and it's part of what will end up being required for your regulatory story. So I think that's a really important thing to consider when making decisions about what kinds of assays make the most sense for your company, and for your where you're at in your drug discovery journey. Um, I've put on here that if you have this specific program and you think that this could be useful for your program, please reach out to the Mosaic team, um, and we'd be happy to connect you with one of our scientists, including myself, to talk more about what you're looking for.